Okay, Newton's method of approximations, and Newton's going to come up a few times in this course in terms of concepts that he proved, and you're going to have the result to work on, okay? That'll come more in the calculus section, yes.
Do we do particle physics?
Particle physics, no.
Do we do stuff with particles? I'm reading the textbook and I saw
in
like...
terms of projection of a particle, yes. Yeah, you look at acceleration, you look at velocity, you look at displacement, you look at simple harmonic motion of a particle, you look at projectile motion of a particle, etc., etc. It's actually good fun. You'll like it, right? You both will like it. That's my tip.
Physics, what's it doing in math? Oh, wonder.
No, I reckon you'll look at it. That'd be pretty cool. Okay, so if x equals a is close to the root of the equation, so we've got an approximation of the value for the root, okay, of f of x equals 0, then the x-intercept of a1, okay, of the tangent at a. Alright, so we've got an approximate solution at a. X equals a, we're approximately close to 0. Alright, if we put a tangent to the curve at that point, alright, usually, not always, okay, the tangent will provide a better approximation to the root. Okay, so here's the actual root, and the tangent in this case will provide a closer approximation for the x value where the root is. Okay, usually, not always, alright, because you think of the curve, it's following some pattern either that way, or you're going this way and you take the tangent there as well, you can have a closer approximation as well depending on where the roots are. Alright, so usually, not always. So your formulas here that involve differentiation, okay, because the derivative of course gives us the equation of the gradient of the tangent. So the next approximation, so A1 is the current approximation, so whatever the value for A is, take away the function at A, okay, over the derivative, the first derivative of A, okay, where A is close to, x equals A is close to the root. So, the equation x cubed plus x squared plus x, take away 8, has a root near x equals 2. Okay, so sometimes you need to establish the value, sometimes you will be told what the value is. So we need to use Newton's method with 2 applications. In other words, use that formula twice to find a better approximation. Alright, so A is 2. That's our first approximation. Okay, so A1 is going to equal 2, take away f of 2 over f dash of 2. Alright, so we need to do a couple of things first. We need to substitute for f of x, for f2, sorry, when x equals 2. And we also need to differentiate this and then substitute 2. Okay. So, you can do one of two things. You can either substitute as you go in the formula, or you can do that substitution to the side and then do your result into the formula here. Alright. So, f of x, I'm just going to put it to the side just so we're not getting too messy here. Okay, so from the question, x cubed plus x squared plus x take away 8, f dash of x, okay, so I'm going to differentiate. Okay, we're not doing integration, we're going the other way, differentiation. So what is my derivative function? So bring down the power, take one off the power. And of course any constant, the derivative of any constant number is 0. Okay? Alright, so f of 2 going to be 2 cubed plus 2 squared plus 2, take away 8. 8 plus 4 plus 2 is 14, take away 8 is 6. F2 is 6, that's what I'm going to put on the top of the fraction. Okay, and f dash of 2. Going to be 3 lots of 2 squared plus 2 lots of 2 plus 1. Okay, 12 plus 4 is 16 plus 1 is 17. Okay, so your A1 okay, it's going to be 2. Take away f of 2, which is 6, over s dash of 2, 17. Okay? That's 34 on 17, equals 6. It doesn't simplify any further, I think. No. Okay, so that is the x value that will give you a closer approximation to the root. Okay? Now, the formula said use the method twice. Okay? So, what you need to do is use your new value. So, A2 can be A1, take away the function at A1 over the first derivative at A1. Okay, so again, you can substitute on the side and put the result into the formula, or you can use all this into the formula if you wish. Okay. So 28 on 17. Right, so f of 28 on 17 and s dash of 28 on. So using the same formula as above. Alright, we work those two bits out. The ever reliable calculation skills of Robin.
Or 4,068 over 4,913.
What?
This will probably need to be a stored calculation. What was it? 0.828. Okay, so as long as you're showing some part of the calculation, but use the whole calculation in your answer. Okay, and f dash of f dash of 28 over 17. Whew.
12.43252595.
So at least show the first part of the calculation, or you're going to write f of 28 over 17 over f dash of 28 and 17. Okay, so show that substitution. Alright, what does that all simplify down to? The question would probably be saying what, how many decimal places to round to? One point 580, was it? Alright. Alright, so I'm going to state two decimal places. Alright, so the original root was approximately, the original approximation is 2. Alright, after 2 applications, we've been able to get a better approximation. Okay, that's the whole process. There. Alright, use Newton's method, twice, with 2 applications, to find the square root of 2 decimal places. Alright, so, is that saying x equals square root of 2? Okay, what would if that was the solution to your root, what would the equation been previously, so going backwards?
It is the same equation.
What equation would I had to solve that my solution would have been square root of 2? Okay, to get the square root of 2, I would have had to take the square root of both sides.
That was the problem.
Okay.
That was the problem.
Nope. Oh, yes, so. Okay, so if I've taken the square root of both sides, it means I had something squared on both sides. Okay, so if I square both sides, so going backwards, so x squared take equals 2, and x squared take away 2 is 0 is going to be where the root came from, the equation to get that root. Okay, so that's what you need to think about first. Alright, so the root came from, to find the square root of 2. The square root take away 2 is 0. So now we need to establish where approximation to that root is. Okay? So, which integer would be the closest to the root for that parabola? Pardon?
Closer to 1.
Be closest to 1, yeah. Okay, because the square root of 2 is 1.42, something like that. Okay, so we're closer to 1. So you think about your sketch, or your parabola, the x squared take away 2. When we solved for that, we got the square root of 2 and the negative square root of 2. Right? So using almost your halving the interval process, we've got f of 1, which is going to be negative, and f of 2, which will be positive. Okay? So I'm going to take x equals 1 as closest approximation. The closest integer approximation. Right, so A1 is going to be A take away f of A over f dash of A. So it's going to be a bit nicer to differentiate and substitute, okay, because it's only much smaller. Very good. So A1 is going to be the first approximation, which is 1, take away f of 1 over f dash of 1. You still have to remember your proving work, boy. Okay, so f of x is x squared take away 2. Right, so f of 1 is going to be 1 squared take away 2, which is negative 1. So f dash of x is 2x. So f dash of 1 is going to be 2. Okay, so equals 1 take away f of 1 to be negative 1 over positive 2. Okay, this is 1.5. 1.5 exactly for what we've just done there. Okay, that is your first approximation. The question asks you 2 application. So that becomes your new approximation. So we've used 1, we now use this value for your next approximation. Okay, so in other words, A2 can be A1 take away f of A1 over f dash of A1. Okay. Okay, so 1.5 take away f of 1.5 over f dash of 1.5. $2.25. Right, so 1.5 take away, so we've got 2.25 take away 2. So it'd be 0.25 over f dash of x is that, 9 over 4 becomes 9 over 2. Sorry, 2 times 1.5. Hang on. 2 times 1.5 is 2 times 3. So it's 3. So 1.5 take away 112. 17 on 12, which is approximately equal decimal form. Decimal form.
1.41666666.
Two decimal places. Okay, what is the square root of 2?
1.41421356.
So 0.01 off with 2 applications of Newton's method. Okay? Right, so that now covers polynomial.